Good morning, ladies and gentlemen. I can't be here today, so I'm going to go over those notes. Ms. Dorsey is going to hand you out a copy of the notes, and I'll go over what to put in the blanks, fill them out so you can write. A lot of it's going to be what we talked about yesterday. We're going to go a little farther with it, and you're going to see a few more things. So the first thing we'll look at, first we're talking about subsets of real numbers and interval notation in this lesson. At the end, you'll have an online quiz that you can take for your homework grade. So the first blank, what are, we talked about this yesterday, real numbers? Told you before, sounds kind of crazy that we name certain numbers real, but it's just a name. But what does it mean when we say certain numbers are real numbers? What does that imply? It implies they're non-real numbers. Doesn't even make sense really if you think of the name real numbers literally in the English sense. But we're going to look at this set of real numbers. The name real numbers as just that, a name, in light other than the strict literal English meaning of the words real and number. Because non-real numbers are definitely real in an English sense, meaning that they exist, but they don't have a name that implies they exist. They don't fit the definition of numbers that carry the name real numbers. We talked about the coconuts, we talked about the way we counted, we talked about the way we came up with the numbers. You can read all this other stuff in here between the blanks. Got all this coconut, all of a sudden we got the real numbers. So what is the definition of real numbers? I don't know that we ever really came up with this yesterday. We talked about it, we worked around it, short day, took away from us. But the set of all real numbers consists of all the numbers you can express as a decimal. Use them to measure number of units from a position designated 0 on a line to another point on a line. The number of units considered positive on the right side of 0, negative on the left side of 0. These numbers can have a decimal part equal to 0, a terminating decimal part, an infinite repeating decimal part, or an infinite non-repeating decimal part. I didn't tell you this yesterday. We talked about some symbols for other subsets of numbers, but the symbol that we use to represent the set of all real numbers is this big, what I call a double-legged R. So when you see that big, funny-looking R, you know we're talking about the real numbers. A set, we talked about this. A set is a collection of things. We're going to refer to a set of numbers. An element in the set. The number 3 is an element in a set of real numbers. Individual member of a set is called an element, and any member of the set of real numbers is also called an element of the set of real numbers. I know this is writing the same thing a lot, but I believe that repetition in this, we talked about this the other day, helps you learn stuff. We have a symbol that indicates that a certain number is an element of a certain set also. That symbol looks almost like an E or a backwards 3. It's actually a Greek letter epsilon. When we write 5.3, then that funny symbol with the big R for a set of real numbers, that says 5.3 is an element of the set of real numbers. Now we're going to talk about subsets. We discussed this a little bit yesterday. A subset of real numbers, a subset of a set. It's a set of elements, all of which are elements of another set. It's a set within a set. I think that's a definition you all came up with yesterday. This looks like a C kind of, or a sideways U, or sometimes it'll be that same symbol with a line under it. I've seen it denoted both ways in books to mean the same thing. A C with a line under it, or just the C by itself, but it means subset. Translated, is a subset of. If we look at a few examples of subsets, we talked about some yesterday. The numbers, counting numbers, what did we call those? The natural numbers. And the symbol, we had that funny looking N with the big double legs. So if we write the statement 4 is an element of that big N, that's translated 4 is an element of a set of natural numbers. And the statement, that big N, subset symbol, big R, says the natural numbers, set of natural numbers, is a subset of the set of real numbers. Then we looked at another set of numbers, negative, positive, whole numbers, and zero, and we called that the set of integers. The symbol for the integers we said was this big funny looking Z. Examples, there are some up there. Somebody, I think Drake, said negative 32. I remember Olivia said 6 and 4. We had all kinds of examples. You can come up with an infinite number of integers. The next subset of real numbers we talked about, set of all real numbers, it can be written as A over B, where A and B are both integers, B not equal to 0. What did we call those? We called those the rational numbers. We had a little fun proving yesterday that any repeating decimal could be written as a rational number. Symbol for the rational numbers is this big funny looking Q. Examples of numbers we could write. We could write the square root of 4, the square root of 9/4. We could write 2.3, negative 5.7. 7 is a rational number. Anything that can be written as a fraction. Square root of 4 is equal to 2, so that's also equal to 4 over 2, written as a fraction with an integer in the numerator and denominator. Square root of 9/4 is the same as 3 over 2. That's already in the form integer over an integer. 2.3, we could write that as 23 divided by 100. Sorry, divided by 10. 23 divided by 10, that's in the form integer over an integer. Negative 5.7 we could say is negative 57 divided by 10. That's in the form of an integer over an integer. 7 is the same as 7 over 1. There's a whole lot of examples, and we showed yesterday that any non-repeating decimal, or any repeating decimal could be written. We're not going to go through the proof right here for this. I'll bore you on the video. But this is also an element of the rational numbers. That leads us to another subset that someone mentioned yesterday. If there are rational numbers, it almost follows naturally that there are also irrational numbers. Remind me tomorrow, and I'll show you a little proof that irrational numbers exist. Tell you a little story that goes along with it. Irrational numbers. Some books use an I, a big funny looking I, to represent the set of irrational numbers. I don't like that because we use the I for other things. So I'm just going to leave it and say we're not going to use a symbol. I don't have a symbol that I use to represent the irrational numbers. But irrational numbers are basically any number, any real number that's not rational. Any real number that's not rational is an irrational number. You can recognize these non-terminating, non-repeating decimals or irrational numbers. On some standardized tests, you'll see a number like 1.12, 112, 1112, and then you'll see a dot, dot, dot thing. Shows that the pattern repeats, but there's never a place where that pattern repeats because of the increasing number of ones between the twos. Never a place where that pattern repeats where we can draw a line over it. So this is an infinite decimal that never establishes a repeating pattern. Therefore, it's going to be an irrational number. Also, any square roots or radicals that can't be simplified. The square root of 2 is an irrational number because you can't reduce it to get rid of the radical. square root of 50 is an irrational root, or an irrational number, because the square root of 50 can be reduced. It can be written as the square root of 25 times 2, which is the same as the square root of 25 times the square root of 2, which is the same as 5 times the square root of 2, but you can still never reduce it to the point where that radical is gone. Therefore, the square root of 50 is an irrational number. When we represent the set of real numbers, we can use the real number line. We looked at that yesterday. We started with that. The real number line models the set of real numbers. And every real number has a location on the line. Every real number is represented by a point on the line. Real numbers have order. That means if any two numbers, A and B, are on the real number line, and A is to the left of B, on that real number line, again, repetition, then we know A is less than B. The order on the number line matters. Certain subsets of numbers can be represented graphically using interval notation. Using a real number line. Graphically, certain subsets of real numbers can be used using a real number line. Sorry, forgot what goes in that blank there. Specifically, we're going to look at how intervals can be represented on that real number line. Intervals, like a part or a section of the number line. If we wanted to refer to the subset of real numbers that was between A and B, all the real numbers included between A and B, we need a way to represent that. On the number line, you might have in the past said, well, if it's between and we don't include A, and between and we don't include B, then we would shade all that space in between and put empty circles on the A and the B, and that would represent all of the numbers between A and B on that real number line. An interval refers to all the numbers included on a section or a segment of that number line. It can be all the real numbers less than 2 represented with the empty circle on the 2 and shaded all the way to the left. 2 on this situation we call the end point of the interval. The open circle indicates 2 is not included as a member of the set, and the shaded section of the line indicates all the real numbers that are covered by the shaded section or elements included in the set. We use a number line to represent the set of all real numbers greater than or equal to 2. Instead of an empty circle, we use the solid circle on the 2 now on the end point and shade greater than to the right. So this represents that all of the real numbers greater than 2 are included in this, greater than or equal to 2 are included in this set. Solid dot says is included. If we want to see a number line represent all the real numbers that are greater than -3 but less than 2, we can put an empty circle on the -3, an empty circle on the 2, and shade in between, and see that set is represented graphically, represents all the numbers less than 2 but greater than -3. And the endpoints again are not included. Use that number line to represent a set of all real numbers greater than or equal to -3, but less than or equal to positive 2. Close circles this time on the endpoints, and the shaded in between says all those numbers in between and the endpoints are both included. If you want to use the number line to represent the set of all real numbers greater than or equal to -3 but less than 2, then less than 2 we put an empty circle on the 2, greater than or equal to -3 we put a solid dot on the -3, and we shade in between, and now we see that we're representing all the numbers between -3 and 2, not including 2 but including -3. Interval notation is another way we represent these subsets of the real numbers. All the real numbers greater than or equal to -3 but less than 2 represent a subset of the real numbers, a set within the entire set. Another style of notation you need to be familiar with, interval notation. It uses brackets, bars, inequalities, parentheses. Oh, this is not interval notation. This is set notation. We call this set notation. Sorry. Set notation on this one. This is an example of set notation. What I call the little squiggly bracket, X, this vertical bar, says negative, then an inequality, negative 2 is less than X is less than 2, and then close the squiggly bracket. You read this, the set of all real numbers X such that negative 2 is less than X is less than 2 means, if we look at this on the number line, negative 2 to 2, because it's greater than X is greater than negative 2 and less than 2, we're going to put empty circles on the endpoints and shade in between. And those are the numbers represented. If we look at the X, this is a set, all real numbers X such that X is less than or equal to 2. There's 2 on the number line. Put a solid dot because less than or equal to, and then we shade to the left because it says less than, and that represents all the real numbers that are less than or equal to negative 2, or sorry, positive 2. We do the same thing here. X is greater than 2. Greater than means an empty circle. Shade to the right. To set X such that negative 2 is less than X is less than or equal to 2. That's all the numbers in between those endpoints, including 2 but not including negative 2. So this is a way you can read set notation. Sorry for the confusion there. Interval notation. Now we get to interval notation. Represents certain subsets of real numbers. It's interval notation. And in interval notation, it's only useful when you're describing a subset of real numbers that's made up of one or more intervals on the number line. We can't represent the integers. We can't represent just the rational numbers. We can't represent just the natural numbers using interval notation. It's only good for segments or sections that include all the real numbers included on that section or segment of the real number line. So when we look at this, we use negative infinity as a left, I hesitate to say endpoint because negative infinity is not a point, but it means the numbers stretch all the way in the negative direction, and positive infinity if the numbers stretch all the way in the positive direction. We're going to use parentheses and brackets. The parentheses in interval notation indicate that the endpoint, the left endpoint here, is not included. So here, if we're looking at the set, let's look at this one. Let's look at numbers from 3 to 4. 3 and 4 on a number line would be the endpoints of this interval. The parentheses indicate that this endpoint is not included. So if you were going to represent all those on the number line, you'd put an empty circle. The bracket indicates that it is included. So we would put a solid circle on the 4, and then all the numbers in between those two endpoints are included. So this is the set of real numbers represented by this parentheses 3, 4, close the bracket. That is interval notation for this set of real numbers. Here, we always put a parenthesis with negative infinity. I'll explain to you why that is in class. But this tells me that 2 is not included. So this is the same as the set of all real numbers that are less than 2. If we look at it on a number line, there's 2, less than, because the parentheses tells us it's not included, and less than tells us to the left, and we shade forever in that direction. So negative infinity to 2 is all the real numbers less than 2. when we go from -2 to infinity, but we put a bracket with -2, that means all the real numbers that are greater than or equal to -2. So if we were going to do that on a number line, we would have -2 greater than or equal to, tells a solid circle, shade to the right. Those are all the real numbers that are represented by this set in interval notation. If we do here, from -3 to 2, not including -3, but including +2, that's all the real numbers that are greater than -3, but less than 2. And on a number line, -3 and 2 are the endpoints, less than or equal to 2, sorry. Greater than, because this is a strict inequality, less than or equal to means we get a solid dot here and we shade in between. That's the way we represent the set using interval notation. And that's the end of that lesson, and that's what you can do to answer the quiz that's on Google Classroom.